Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is general industrial safety. Our objective today is to provide a brief overview of general industrial safety. We'll discuss emergency preparedness, lockout and tagout procedures, personal protective equipment, as well as special case industrial safety scenarios like work at heights, confined spaces, and fluid power systems. Additionally, we'll discuss laws, codes, and governing bodies associated with industrial safety. This lecture does not cover electrical safety, a topic worthy of another independent discussion, which necessitates at least a basic understanding of Ohm's law. First things first, industrial safety is far too important to be covered in a single online lecture by an individual that is not even remotely qualified to do so. If you are wishing to obtain safety certification or gain in-depth knowledge about this subject, visit your local community college or a recognized and reputable independent service provider. This lecture's only purpose is to provide a general overview of this topic. My intention is that you understand, appreciate, and most importantly, respect industrial applications of energy in its various forms, not fear it. Energy is as dangerous as it is useful, and there are laws, natural and man-made, that govern its wise use. Before we begin, I'm going to take the unusual step of compressing all these topics we're about to discuss into one easily memorable statement. Know what you're doing. Don't just flip switches and push buttons. You're going to get yourself or someone else killed. Your lab partner is here for the same reason you are. They want to learn. They're just doing a horrible job at it because they can't show up to lab prepared. A lot of industrial accidents aren't caused by careless or reckless people. Sometimes industrial accidents are caused by well-meaning people simply lacking the knowledge to do the job they've been pressured into doing. Don't do things you don't understand. I am more than willing to admit there are things that I can't do or don't understand, like listen or care about people's feelings or any of that other made-up stuff. I just don't do it well, and I'm not going to pretend I do. If you're being pressured into doing something you don't understand, don't do it until you're absolutely clear no one is going to get hurt. People's lives might be on the line, and one of those lives might be yours. Think about it. Imagine going home every night, safe and sound, because you know what you're doing. Again, this lecture is not meant to cover all aspects of industrial safety, nor take the place of a safety course delivered by a certified trainer. This is only meant to serve as an orientation of the subject. This general orientation is going to cover the following topics: emergency preparedness, including a discussion on first aid, CPR, and AED, lockout and tagout procedures, personal protective equipment, special case industrial safety scenarios, including work at heights, confined spaces, and fluid power systems, and finally a brief orientation of laws, codes, and governing bodies. Let's get started. Emergency preparedness. The Boy Scout motto says it most succinctly: be prepared. Be prepared and be always in a state of readiness in mind and body to do your duty. Be prepared in mind by having disciplined yourself to be obedient to every order, and also by having thought out beforehand any accident or situation that might occur so that you know the right thing to do at the right moment and are willing to do it. Be prepared in body by making yourself strong and active and able to do the right thing at the right moment and do it. Yeah, I was an Eagle Scout. Can you tell? Leaving aside the transparently fascist encouragement to obey orders without question, I never said I was a good Eagle Scout. We're left with some very good advice. Think of all the bad things that can happen. Come up with a plan to mitigate their effects, and have the training and equipment necessary to execute the plan. Hope for the best, but plan for the worst. One need look no further than the military for example of preparation and preparedness. Soldiers are daily drilled in small and large unit tactics and trained in the maintenance and field expedient repair of all sorts of weaponry. The tasks after a time become ingrained habit. They become not thought, but reaction. Equal importance must be placed on planning and preparation as civilian industrial environment. It must become second nature. The difficulty is that civilians don't unquestioningly obey orders. You got to spend a little bit more time bending these fickle mushheads to the purpose of creating a coherent and executable action plan. My professional background is in renewable energy, so I'm going to use a wind farm as an example regarding planning and preparation for emergency events. Communication is key, especially so considering turbines comprising a wind farm are often distributed over a wide geographic area. The operations and maintenance building needs to have communications with teams in the field, Teams need to have communication with other teams, and members of the same team must be able to communicate with each other while performing assigned tasks. Every single truck needs to have a radio, a first aid kit, a fire extinguisher, and a rescue and evacuation kit. And every technician needs to know how to use them. Every team needs a map with every single wind turbine on it, as well as all roads, inclement weather shelters, evacuation routes, and the location of special purpose medical equipment like stretchers, backboards, and AEDs. On the back of the map should be all emergency procedures and contact numbers. The map needs to be laminated, and technicians need to be responsible enough not to let the map blow away. Don't laugh, it happens. Wind farms are windy, go figure. Now think beyond the map. The wind farm is not an isolated entity. Emergency preparedness must be expanded beyond its confines into the local community. Every single hospital, ambulance service, and medevac unit in the area needs to have the same map, and they need to know the battle plan for an emergency. Having a map and a plan isn't enough. Inspect emergency equipment on a regular basis. Refresh, retrain, and recertify personnel on rescue and evacuation equipment. Rehearse and drill portions of the action plan. Then put the complete plan into action with scheduled and unscheduled, i.e. surprise rehearsals. Does the plan survive first contact? Or does it fall apart quickly because of some fatal flaw? Identify the flaws, fix them, and test them out again. Planning and preparation is not a static process. It must be continually reviewed and re-engineered. On a very basic personal level, always have an exit plan. Every time you walk into a building, a room, or a public place, or a relationship, I want you to look for at least 3 exits. I know it sounds paranoid, but it's just good practice. What happens if one exit is blocked? What if there's a fire? Where is the nearest fire extinguisher? Where is it? I'm asking you. Where is the closest fire extinguisher to you right now? Find it. Now that you got your fire extinguisher, or pause the lecture and went out and bought one, what are you going to do with it? Step 1, you sound the alarm. Step 2, you don't use a fire extinguisher to put out fires. You use a fire extinguisher to clear a path to one of your 3 exits. Step 3, lead all the people you want to keep to safety. At all times, you need to be able to not think about, but immediately act upon pressing survival level questions. In times of crisis, some ordinarily intelligent and capable people go Tharn, which if you've read Richard Adams' novel Watership Down, you'll recall Tharn means immobility in the face of oncoming danger. It is your responsibility to lead these people to safety. First aid, CPR, AED. Everyone you work with, at a minimum, should be trained in first aid, CPR, AED. This is not a universal practice, but it should be. Learn how to respond to common first aid emergencies, including burns, cuts, head and neck and back injuries. Learn how to respond to cardiac and breathing emergencies using CPR, which stands for cardiopulmonary resuscitation, and an AED, which stands for automated external defibrillator. If this is not already mandatory at your place of employment, make it so. Get the training and get an AED. Your local community college or organizations like the American Red Cross offer first aid, CPR, AED training. Certification typically lasts 2 years. Lockout and tagout. Moving beyond emergency preparedness, let's look at a concept known as lockout and tagout. Lockout and tagout procedures are daily practices that, if followed properly, prevent the emergency plan from ever being initiated. Lockout not only means that one must achieve a state of zero energy while equipment is being serviced, it also means that one must ensure that it remains that way the whole time it's being serviced. Turning off a motor or just unplugging it from a wall doesn't qualify as a lockout, because someone can just walk by and turn it back on or plug it back in. Not exactly the most ideal of circumstances if you're the one doing a shaft alignment on this motor, or if you're the one inside a rotary debarking machine at a lumber mill. Locking it out means exactly that. You are locked out from turning the system back on. This is enabled with locking mechanisms that cover plugs, buttons, or prevent valve handles from being turned. They are then locked into this position by individuals performing maintenance on that system. Here's a lockout device being used on a plug. Here's another lockout device being used on the switch. All individuals working on that system have their own individual lock. In order to unlock it, all individuals must be present and accounted for. This prevents the undesirable circumstance of leaving a coworker inside a machine before it's returned to service. Teams of workers will use the locking mechanism or mechanisms in the case of multiple lockout points and a hasp with individual padlocks. Each worker has their own padlock and their own key. The locking mechanism go on the means of energy isolation. Each worker installs their own padlock and locks it. If more workers are assigned to a single task than there are spaces on a hasp, the last hole is typically reserved for an additional hasp. Achieving a state of zero energy means that there is no source of hazardous energy present, nor can any build up during the course of a maintenance procedure. This is, again, not as simple as unplugging a system. Consider other forms of hazardous energy, including but not limited to thermal, hydraulic pressure, stored hydraulic pressure in an accumulator, stored electrical energy in batteries or components like capacitors, chemical energy, or suspended weights. All these forms of hazardous energy need to be locked out, blocked, or released. Additionally, realized systems are often remotely interconnected, and certain commands can override manual controls. These means of operation must also be locked out. Lockout means achieving a state of zero energy while the equipment is being serviced, and must remain so until returned to service. The concept of tagout is different from that of lockout. Once a device is locked out, a tag accompanies the lock, indicating the system is not to be operated under any circumstances. Additionally, a worker's name, contact information, date and time, and the procedure being performed is often written on that tag. Here's where it gets tricky. A tagout has the same purpose and importance as a lockout. If you can't lock a system out, you tag it out, and no one is supposed to operate the system while it's tagged out. This may seem a little risky, and it certainly is if you regularly work with people untrained in lockout and tagout procedures. Realize there are systems still running that are built way before lockout and tagout procedures became law. These systems cannot be locked out and must instead be placed in a state of zero energy and then tagged out before being serviced. At no point should a tagged out system be operated until all workers owning the applied tags remove them. The success of the tagout system is dependent upon a trained and disciplined workforce. The general procedure used to prepare a system for service follows this scheme. You might see textbooks or attend safety certification training that uses more or less steps, but they follow the same general sequence. Have a plan. Know where all the lockout points are on a particular system and have the means of locking them out available. Your company should have procedures clearly indicating what needs to be locked out prior to performing a service. The workforce should be trained in the use of lockout and tagout procedures. Step 2. Notify all affected personnel and shut down the system. Step 3. Lock out, release, or block all sources of energy that have the potential to unexpectedly start, energize, or release during the course of the procedure. This includes means of remote operation. Step 4, and this is super important, verify the system is isolated. Trust no one. Your life is on the line. Use your voltmeter to perform voltage checks. Read pressure gauges. Look at the thermometer. Check to make sure any lifted weights are blocked out or lowered. Don't just assume things are safe before you begin work. Step 5. Now that you've verified the lockout and tagout procedure was successful, you can perform the service. If you're doing a shaft alignment or oil change, you can do so and don't dilly-dally. Step 6. Once the procedure has been performed to your satisfaction, you can start cleaning the area and notify affected personnel you'll be returning the equipment to service. Now that the area is all clean and all maintenance personnel are accounted for, you can begin removing the lockouts and tagouts. Step 7. At this time, the serviced equipment can be inspected for proper functionality, and if given the green light, can be returned to service. Notice not only the use of lockout and tagout procedures, but the coordination that occurs throughout this sequence. At no time does machinery suddenly just start, stop, or start again. Everyone is made aware of what's going on, and no one should be surprised. That's the real purpose of a lockout and tagout procedures. Make people aware that lives are on the line and the system is not to be operated while it's being serviced. Let's move on to our next general industrial safety topic, personal protective equipment. Personal protective equipment. Certain work environments pose environmental or industrial hazards and sometimes require special equipment and attire appropriate to the situation. This could be as simple as wearing a jacket in the winter and not wearing one in the summer. Personal protective equipment, sometimes known as PPE, goes beyond just the wise choice of outerwear and often includes head protection, eye protection, hand protection, special protective clothing, ear protection, foot protection, and fall protection. We'll cover each one separately, but a general rule applies to all categories. Inspect your personal protection equipment every single time before you use it. No sense in jumping out of a perfectly good airplane if your chute is just a backpack stuffed with old newspapers. Personal protective equipment that does not pass inspection must be disposed of and a replacement obtained before work can begin. Let's start at the head and work our way down. Head protection. The hard hat's obvious purpose is to protect an individual from head injuries, notably dropped objects. People often assume the most common safety incident involving wind turbines is that of injuries sustained from falls. This is incorrect. The number one safety incident involving wind turbines is dropped objects. Safe work practices and a disciplined workforce that routinely tethers and ties off all tools, radios, or equipment must be developed. The hard hat protects an individual from this avoidable error. The standard that governs hard hats is ANSI Z89.1. Type 1 hard hats only protect against impacts to the top of the head. Type 2 hard hats, noted by a brim around the perimeter, also protect against impacts to the side of the head. Additionally, the brim serves to shade an individual under the hard hat. So these types are often preferred by individuals that work outside in the renewable energy business, notably wind turbine technicians and solar installers. In addition to type, hard hats are differentiated by 3 different classes: G, E, and C. A general or G-class hard hat can protect up to 2,200 volts or 2.2 kilovolts, and an electrically protective or Class E hard hat can protect up to 20,000 volts or 20 kilovolts. A Class C hard hat is a conductive hard hat that, for obvious reasons, isn't used in environments with electrical hazards. These are primarily used in industrial environments like metal smelters, where an errant droplet would just melt through a plastic hard hat. Eye protection. Impact-resistant safety glasses with detachable or integrated side shields, goggles, or face shields are designed to protect the eyes from errant foreign objects. All eye protection is governed by ANSI Z87.1 and must state this on the frame. Goggles and larger safety glasses are designed to be worn over prescription glasses. Prescription glasses do not take the place of safety glasses and must be specially designed and approved by the ANSI Z87.1 standard if they are to perform this role. Common hazard to the eyes in an industrial environment might include airborne particles, pinhole leaks in pressurized systems, explosions, or other similarly undesirable circumstances. If you've ever used a pneumatic nail gun before and disconnected the hose under pressure without holding onto it, you are no doubt aware of the phenomenon known as hose whip. Where does the heavy metal coupling go? It shoots straight into your eye. This is true no matter how vigorously you zag or zig. Put some safety glasses between you and that hose and hold onto it when you disconnect it. Face shields are meant to accompany safety glasses with side shields. If you've ever used an angle grinder with a cutoff wheel before, you realize hot metal particles will still find a way into every opening on your clothing, and having at minimum a double layer of protection over your eyes is extremely wise. Every time I use an angle grinder, I put a face shield over goggles over safety glasses and I keep my eyes shut. Hot, sharp metal shavings in the eye are bad news. It's also bad news to be around me when I'm using an angle grinder because my eyes are closed. Face shields can also be used in chemically hazardous environments used to protect against splashes, spills, and drips. As a second line of defense, making an eye wash station immediately available is also a recommended practice. In the event a particle does enter an individual's eye, The eye wash station is designed to flush out the particle quickly. Sometimes full-blown emergency showers are used in industrial environments containing chemical hazards. Hearing protection. Sometimes industrial environments are pretty noisy, and steps need to be taken to prevent instantaneous or gradual hearing damage. An earplug is a soft, moldable device that fits inside the ear canal and then expands to protect the inner workings of your ear. Don't try to fit them anywhere else or even suggest sharing earplugs with another person. An earmuff is an over-ear device. A common unit used to measure sound is the decibel. Both earplugs and earmuffs have a noise reduction rating, sometimes initialized as NRR, that reduces the environmental noise by that amount. As an example, consider a 90 decibel sawmill, and you're using an earplug with a 30 decibel noise reduction rating. This earplug will reduce the sound to 60 decibels. But that same 30 decibel noise reduction rating earplug will only reduce the sound of a departing jet from 140 decibels to 110 decibels. This is where it gets a little tricky, because OSHA requires individuals to be exposed to less than the time-weighted average of 80 decibels over 8 hours, meaning one could be exposed briefly to loud sounds in excess of 85 decibels or continually exposed to levels of sound less than 85 decibels, as long as the average over 8 hours does not exceed 85 decibels. Protective clothing. At a minimum, clothing should be chosen that is resistant to abrasion, chemicals, and fires. Obvious environmental considerations require that you stay warm or cool depending upon the season, but flammable clothing, or worse yet, clothing that melts when it's on fire, is not authorized on the job site. Special circumstances sometimes require high-voltage sleeves or even arc flash protection suits if involved with high-voltage switching operations. Hand protection. Choose the right glove for the job. Cut and abrasion-resistant gloves used to climb a ladder on a wind turbine aren't the same gloves you'd use to perform high-voltage work, nor are these the same gloves you'd use in a caustic chemical environment. Chemicals react to different materials differently, and you must choose gloves that protect from the specific chemical hazard being presented. No sense in wearing acid-resistant gloves if you're handling sodium hydroxide, a strong base. The same advice holds true for rubber gloves that are often used as insulators for electrical work. Different gloves have different voltage ratings, and you need to use the glove with the right rating. Rubber gloves are especially fragile, and even a pinhole leak renders the whole glove useless as an insulator. It is for this reason they're supplied with leather overgloves. A quick and easy function test on the inner rubber layer is to see if air trapped in them leaks out. If so, get a new pair, because these won't protect you against electrical hazards. As a general rule, gloves, and for that matter any PPE, should fit as snugly as possible to get the job done. The reason is you might be working around mechanical hazards such as moving shafts and meshing gears. Any loose or ill-fitting PPE stands a larger chance of getting caught or sucked into such a hazard. This is especially true for individuals wearing fall protection equipment such as shock-absorbing lanyards. When you put this equipment on, you are now a two-tailed monkey, and you must at all times make sure a lion isn't going to grab one or both of your tails and pull you into its mouth. Make sure all machine guards are in place around mechanical hazards and watch out for lions. Foot protection. Industrial environments are especially unforgiving on feet, so it is a common practice to wear safety toe boots with oil-resistant soles. The safety toes prevent impact injuries, and the oil-resistant soles aren't destroyed by oil, in addition to providing slightly increased traction on oily surfaces. The standard governing foot protection is covered in ANSI Z41. A shout out goes to both Danner Boots and Keen Footwear in Portland, Oregon for making awesome boots in the United States. No, I do not receive a kickback from these guys. Believe me, I wish I did. But I think supporting manufacturers that play on the same team you do is the right thing to do. Among the many compelling reasons why I'm such a strong advocate for renewable energy is because it cannot be outsourced. Moving on, let's look at 3 special case scenarios for industrial safety: fall protection work at heights, confined spaces, and fluid power systems. Fall protection. This is a special personal protective equipment category for individuals that need to perform work at heights, like wind turbine technicians, linemen, or solar installers. A fall arrest system is required if any risk exists that a worker may fall from an elevated position greater than that of 6 feet. Typically, a fall arrest system is composed of a harness and a shock-absorbing lanyard. Ideally, the fall arrest system should only come into service should a fall occur. Bottom line up front, wearing a harness will not prevent you from falling. It will, however, mitigate the effects of a fall if combined with a shock-absorbing lanyard and a solid anchor. A full-body harness distributes the fall forces throughout the body and keeps a victim upright and conscious in the event of a fall. The shock-absorbing lanyard decreases the total fall-arresting forces. Outside of the fall arrest system, a number of other supporting devices are used in work-at-height scenarios. Ladder climber. A ladder climber is a camming device that allows upward and downward travel along a secure cable or rail. However, upon rapid descent, the camming device is activated and locks the climber in place. Here's a ladder climber being installed on a cable. The ladder climber can go up and down. However, rapid descent, the camming device is activated and locks the climber in place. Here's a ladder climber being installed on a rail. Again, it allows upward and downward travel. However, rapid descent locks the climber in place. Suspension trauma mitigation straps. Suspension trauma mitigation straps are devices that are deployed in the event of a fall. A worker suspended from a harness for any length of time can have deoxygenated blood pool in their lower extremities and be quickly rendered unconscious. These straps are used to allow a worker to move into a more comfortable position and assist in their own rescue. Here's a clip of suspension trauma mitigation straps being deployed and utilized. Work positioning lanyard. The work positioning lanyard is an additional adjustable lanyard used to hold a worker in place while keeping both hands free to work. Here's a clip of a work positioning lanyard being used on a ladder. The work positioning lanyard is not designed for fall arrest purposes. Whenever the worker leans back, the system is activated. In addition to this use, the work positioning lanyard can be creatively employed as a backup set of suspension trauma mitigation straps. It can act as a tether, a rope deviation, or aid in the lateral transfer of a casualty. I fully admit I was skeptical upon first seeing these come into the workforce, but I am now a true convert. The utility of this device in work-at-height scenarios is only limited by your imagination. Here's time-lapse footage of an unusually handsome individual donning appropriate personal protective equipment for work-at-height scenarios. Notice the hard hat with the security strap, safety glasses, harness, gloves, the ladder climber, the fall arrest lanyards, the suspension trauma mitigation straps, the work positioning lanyard, and the safety toe boots. In addition to this individual personal protective equipment for work-at-height scenarios, there exist devices for retrieval, rescue, and evacuation. These allow for the retrieval and rescue of a coworker in the event of a fall. These devices are manually activated assemblies with a gear ratio that allows a single person to pull a casualty from the fall arrest system and safely lower them to the ground. Here's a clip of such a device being used for this application. Additionally, some of these devices can be used to rapidly evacuate elevated environments and descend to the ground safely. Here's a clip of a device being used for such an application. Additionally, special purpose evacuation only kits, as well as portable multi-purpose kits, are becoming more and more commonplace in the wind turbine technician field. Additionally, a pre-roped pulley combination is an excellent addition to your rescue kit, as well as several pulleys and additional carabiners and slings. The pre-roped pulley combination can be used to laterally transfer a casualty to a more convenient evacuation point, or can be used to assist in transferring a casualty around, over, or under obstacles. The pulleys, carabiners, and slings allow for rope deviations without compromising the strength or integrity of the rescue device or the rope. Again, creativity is often key to the success of difficult rescue or evacuation scenarios. Having the tools available when you need them and the training necessary to use them is part of a good safety plan. A final note about work at height scenarios is to be aware. Be aware of things above you. Never walk under a suspended load or stand below people working. Be aware of people working below you. Always tether tools to you. This sounds stupid, but I'm serious. Be aware of bees. If there's one thing bees love more than stinging you, is stinging you while you plummet to your death. A face full of angry bees, an ordinarily harmless cut, a minor electrical shock, or just a hammer to the thumb becomes life-threatening when working at heights unprotected. Confined spaces. Let's move out of our discussion of work at heights and into an enclosed or partially enclosed space not intended for human occupancy. I'm of course talking about confined space safety in industrial environments. Confined space is recognizable as one that 1. Is enclosed or partially enclosed space not intended for human occupancy. 2. Has a restricted entrance or exit due to size or location or means of access. Number 3, can represent a health or safety risk due to its design, construction, location, contents, or atmosphere, or because of the work that is being performed. An example of a confined space would be a manhole, a tank, or a vault. All of these environments will require special safety consideration, attendance, clear and constant communication channels, and special equipment to extract an injured worker from the confined space should it become necessary. Confined space injuries are often multi-fatality events because the natural inclination is to rush in and attempt to save someone. Environmental hazards such as low oxygen or the presence of an invisible poisonous gas must be tested before entering any confined space. You cannot help a casualty by becoming a casualty yourself. Our final special case industrial safety scenario is that of fluid power systems. Fluid power systems are found in most industrial scenarios because of their incredible force and holding power. These same desirable characteristics bring with them special considerations for their safe operation, maintenance, and repair. Fluid power systems are divided between hydraulic and pneumatic systems. Hydraulic systems use liquid as the transfer medium, whereas pneumatic systems use air. The fluid filling a fluid power system is under pressure. Liquids and gases under pressure can do a couple bad things to a container or a hose if the pressure is too high and the container or hose are damaged. 1, the container or hose could catastrophically rupture, or 2, a pinhole leak could develop. The pinhole leak is especially dangerous in the case of hydraulic systems, because that thin jet of high-pressure oil is now a poisonous laser. If one was to cover a pinhole leak with your bare hand, you might lose a finger in the process or be subjected to something called an injection injury. An injection injury is when high pressure forces oil into your body. Such an injury may require amputation of the affected limb or involve surgery. Immediately shut down a hydraulic system if you discover a pinhole leak and never attempt to stop the leak with your hand or any other part of your anatomy you wish to keep. Even if high pressure oil isn't injected into your skin, a pool of slippery oil in the wrong spot may be just as deadly. Spilled oil presents an obvious fall hazard as well as an environmental concern that must be responded to immediately. This is doubly so for exotic fluids used in industrial processes presenting a chemical or flammability hazard. Material safety data sheets should accompany all systems and make abundantly clear any special precautions necessary to limit loss of life or prevent injuries. At all times, consider the clearance of fluid power actuators like cylinder rods or mechanical linkages. At no time should any portion of your anatomy enter the region of travel. Once a hydraulic cylinder extends, it often does so with tremendous force and will punch through metal, not to mention flesh and bone. A commonly used tool in the wind turbine industry is something called a hydraulic torque wrench, which uses an actuator arm that often pushes against the tower wall to tighten a nut. Woe to those individuals that place their fingers between this arm and the tower wall. Be aware of pinch points when using such tremendously powerful tools. A common application of hydraulic systems in industrial settings is to lift or to suspend heavy objects. The lifted or suspended object now represents stored energy, as does the fluid under pressure supporting them. This needs to be taken into consideration when performing maintenance on these systems, and those lifted or suspended objects need to be lowered or blocked out, and the pressure relieved from the system before maintenance operations can begin. Additionally, realize components such as accumulators or springs can store energy in a hydraulic system and also need to be released and locked out prior to performing maintenance. An accumulator is a tank, quite like a spring that pushes on the fluid. The pump may be turned off, but lifted or suspended objects and components like springs and accumulators may still pressurize the system. Fluid under pressure and moving through a system can sometimes present thermal dangers. Compressors in pneumatic systems can be unusually hot during the compression process and equally as cold when being discharged. The oil reservoir for a hydraulic system can be filled with hot oil, and heat exchanger devices can still be warm. Allow time between shutdown and maintenance for these components to cool. There are similarities between hydraulics and pneumatics, but there are also important differences. Do not think for a moment by understanding one type of system, you are also an expert in the other. The principal operational difference between the two types of systems, besides the phase of the fluid medium, is that of actuation speed. A hydraulic cylinder extends continually as incompressible fluid fills the actuator. A pneumatic cylinder has a tendency to rapidly pop into position only after a certain actuation force has been achieved. Be aware of this if working on a pneumatic system and don't get popped. As a final consideration of fluid power systems' unique safety aspects, realize there's a growing use of electrically controlled hydraulic systems. These systems present numerous advantages that can be most accurately summated as the hydraulics are the muscle power and the electronic control is the brain power. Things get bad if your brains spring a leak and your muscles are filled with flammable fluid. Keep your workplace clean. Clean up oil spills immediately. Not only is this an important safety consideration, your boss is less likely to bother you if you keep your assigned area clean. The topic of electrical safety is worthy of its own independent discussion and necessitates at least a basic understanding of Ohm's law prior to doing so. If you're so qualified, by all means check out the electrical safety lecture, available at the Big Bad Tech channel, or just continue on in the sequence as this playlist was intended. Before we wrap up this lecture, let's discuss some of the governing bodies and the laws and codes associated with general industrial safety. Some of these are governmental organizations, so anticipate a lot of acronyms. First and foremost, the U.S. Occupational Safety and Health Administration, otherwise known as OSHA, was created to assure safe and healthful working conditions by setting and enforcing safety standards and providing training, outreach, education, and assistance. OSHA inspectors regularly inspect workplaces to make sure prescribed safety regulations are being followed. OSHA offers several different levels of safety training for several different industries, including general industry, construction, maritime, and disaster sites. OSHA has a strong relationship with another body called the American National Standards Institute, or ANSI. I previously mentioned ANSI in our discussion on personal protective equipment. The best summary I've ever heard about the different roles of these two organizations is that ANSI develops and issues performance standards for products. However, OSHA regulations tells you why you use these products to protect workers. The National Electrical Code, sometimes known by its initials NEC, is a set of rules published every 3 years by another organization known as the National Fire Protection Association, sometimes known by its initial NFPA. The purpose of the NEC is to safeguard people and property from electrical and fire hazards. Standards contained in the NEC are adopted by communities and enforced. Different articles within the NEC govern different electrical installations. For example, Article 430 covers motors, motor circuits and controllers, and Article 690 covers solar photovoltaic systems. These and other articles in the NEC cover almost all aspects of a particular installation and incorporate significant safety factors into wire sizing and other component specifications, again with the purpose of safeguarding people and property from electrical and fire hazards. Nationally recognized testing laboratories, NRTLs, are testing facilities that provide product safety testing and certification services to manufacturers. Examples include Underwriters Laboratory or the Canadian Standards Associations. These are the ones that actually verify that a particular manufacturer's product does what they say it can do. Products that meet these specifications are then listed or labeled as such and can be used to satisfy requirements based on the NEC. Any modifications to a component may void its label or listing and may not satisfy code requirements. Finally, there exist two almost parallel organizations that define and recommend safety, mechanical, and electrical standards for motors and other electrical equipment. In North America, the National Electrical Manufacturers Association, known by its initials NEMA, takes this role, and the International Electrotechnical Commission, sometimes known as IEC, covers the rest. There does exist interchangeability between NEMA and IEC specs, but the two organizations use different units, schematic symbols, and have differing philosophies on robustness and specificity. I'm largely agnostic about the units I apply during this lecture series, but obviously I prefer using the SI metric system with engineering prefixes because of its inherent advantages. Every once in a while I'll throw a couple glass beads and firewater to the cave-dwelling proto-humans who don't use the metric system, and do an example in their anachronistic units just to keep them happy. If you're comfortable doing unit conversion, it shouldn't matter which units I use. Similarly, I am comfortable using either NEMA or IEC schematic symbols, but do have a tendency to default to those that I use most regularly. If I present to you the schematic symbol for a three-phase contactor with an overload, a type of electrical switch, that looks like this, and you see a schematic that says it looks like this, neither of us is wrong. It's just that the symbol on the left is the NEMA version of a three-phase contactor with an overload, and the symbol on the right is the IEC version of a three-phase contactor with an overload. They're kind of the same, and you can see obvious similarities between the two. Here's the coil. Here are the three normally open switches controlled by the coil. Here are the three overloads. Don't think such an easy translation exists for all cases though. As I introduce common components and their schematic equivalents, I'll try to throw in alternate representations every once in a while just to keep us on our toes. This series would be prohibitively long if I did this for every illustrated example, so if I fail to use units or schematic symbols not in accordance with your country's or occupation's methodology, it is your responsibility to do the unit conversion or use the symbols you most often employ. Finally, the philosophical differences between the NEMA and the IEC can be summated as a difference between robustness and specificity. Components like contactors designed by NEMA specifications have a tendency to have a broader application range, whereas those designed to IEC specifications are more selective and purpose-built. Depending upon your application, this could be viewed as an advantage or a disadvantage. Consider a specific application in which there are 9 divisions of available NEMA contactors, and for the same application, 14 divisions of IEC contactors. Each NEMA contactor covers a broader range of acceptable operation points, and each IEC contactor less. The NEMA contactors are more robust, but they're normally bigger and more expensive. The IEC contactors are lightweight and less expensive, but they don't have as wide of an operational range, and you really need to know what you're doing when you're sizing an IEC contactor because numerous operation parameters come into play. Before we close up shop on the topic of general industrial safety, I need to level with you and make one thing clear. I am not an electrician, and you cannot use anything you learn from this or any of my other lectures as professional electrical advice. follow the rules, follow the code. It's there for a reason, to safeguard people and property from electrical and fire hazards. This content has been developed for edification only. While reasonable care has been exercised with respect to its accuracy, I assume no responsibility for errors, omissions, or suitability for any application or misapplication of its contents. This material cannot, will not, and never makes the claim to take place of personalized guidance in a safe and supportive lab environment. At most, this content only serves as bare minimum requirements to even enter a lab. Get in touch with your local community college and see if they offer courses with associated hardware labs. Alright, let's bring this brief orientation on general industrial safety to a close. As a final note directly related to your personal safety, don't be the guy that shows up to a promotional photo shoot for your school or company's industrial training program wearing shorts and flip-flops. Your lab instructor, quite like your mama, always reserve the right, regardless of your age or professional position, to set you on their knee and spank you for being stupid and unsafe. At a bare minimum, show up to lab prepared, wearing closed-toed shoes and long pants. In conclusion, this lecture provided a brief overview of general industrial safety. We discussed emergency preparedness, first aid, CPR, AED training, lockout and tagout procedures, personal protective equipment, as well as special case industrial safety scenarios like work at heights, confined spaces, and fluid power systems. Finally, we discussed laws, codes, and governing bodies associated with industrial safety. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.